So section 5.2, the orthogonal complement and projection, orthogonal projection. So let's start working with examples, and we're gonna write down the rules. That's why I'm always telling you, check the slides. So for the first example, they're telling you to find an orthogonal complement W complement. That means the sign is the complement of W, and give the base for the W complement. W complement, there is a rule that says, if you check the slides, to find the W complement is going to be the null. So let's write down here. W complement is going to be the null space of A transpose. Null space of A transpose. Now, we already have W equal XYZ. They're telling you X is 1/2T, Y is -1/2, and Z equal 4T. So let's work on this one, because W, we need to find W complement. So what I'm going to do, I'm gonna write down W first, and then I'm gonna find A transpose, which is A is the null space, and then after that, the null of A transpose, which is going to be the W complement. So let's do it step by step. W is column space of A, which is equal, that's mean W equal, I'm just gonna let T equal 1. So T equal 1, that's mean the X is 1/2, and the Y is -1/2, and Z equal 4. So X is going to be 1/2, Y is going to be -1/2, and Z is going to be 4. So I'm going to use this rule. That's mean the first thing I need to find, I'm going to let this is the A transpose. That's mean this is A. 1/2, -1/2, and 4. That means A transpose is going to be equal 1/2, -1/2, and 4. This is A transpose. Now we're going to find the null space for this one. If you remember how to find the null space, we're going to take A transpose and solve it. That means the solution. The transpose, the null space is the solution for the matrix. And I have only one row with the 3 columns. So it's going to be 1/2, -1/2, and 4 with the 0. Reduce this one. So by reduction, which is the reduced or echelon form, the matrix is going to be, that's mean you're going to multiply by 2, because we need to the first element is going to be the 1, and this one is going to be -1, and the last one is going to be 8 with the 0. Now, x1 minus x2 plus 8 x3 equals 0. I'm going to solve it for x1. Is going to be x2 minus 8 x3. I'm going to let x2 equal s and x3 equal t. That means x1 is going to be s minus 8t. So our null space of t is going to be, so null of A transpose, which is equal We did this one before. X1 is going to be S minus 8t, and here is S, and X3 is t. This is the null space of A transpose, which is equal S. S is, here's 1, 1, and 0, plus t, and here is going to be negative 8. There is no t here on the second row, and there is 1 on the third row. So here we're going to write down the base here, which is our solution. Now we need to find the base, which is these two columns. That's mean base for W is going to be, this is the orthogonal, and the base, which is going to be these two, is going to be the span of 1, 1, 0 and negative 8, 0, 1. This is going to be the base for the W complement. So how are we going to type it here? I'm going to type it here as a 1 and 1, 0. And we're going to type here negative 8, 0, 1. 0 and 1. Let's check that. We're going to do the same process. So this is the first rule. To find W complement, you're going to find the null space, which is the solution, but for the transpose, not for the matrix A, because you're going to assume that A equal this matrix, and then you're going to find the solution for the A transpose by do the reduction, which is convert the matrix to reduced row echelon form, and then find the solution by the x1, x2, x3. But now with this example, we have only one row with 3 columns. So for example 2, we're going to do exactly the same steps. We're going to find the row space of A, and here's the matrix A, and we're going to find the null space base for the null space of A, but we're going to verify that row space of A is orthogonal to every vector in the null space of A. That means you're going to just do the dot product. You have to get 0. But first of all, we need to find the row base for the row space of A. So first of all, to find the row space of A and the null space of A, we have to reduce the matrix. So let's reduce A with the 0, which is equal the matrix A, 1, negative 1, 0, negative 4, negative 1, 1, 1, 3, 3, negative 3, negative 2, and negative 10 with the 0. Because I'm going to find the null space on the same time, which is the solution. So I'm going to convert all these elements to zeros by multiplying, add these two columns. This is also already 0 times 4 and add with the negative 4. So the first thing is going to be 1, 0, 0, 0, and here is going to be negative 1, 0, 1, negative 1, and 3, 0, negative 2, and 2. There is all zeros here. Then the second operation, we need to change this one, row 3 with row 2 with the 3, because I need to, the first element entry is going to be here. So change this one. So it's going to be 1, 0, 0, 0, and here is going to be negative 23. And this one is going to be 1, negative 2, and 0. And here is going to be 2 zeros with this one is 0, and negative 1, 2, and 0. Then next step, I'm going to convert this one to 0 and this one to 0 by add with row 1 and add with row 3. Yes, so it's going to be 1, 0, 0, 0. And this one is going to be 0, 1, 2 zeros here. And this one is going to change to 1, negative 2, and 2 zeros here. With the zeros, that's it. This is the reduced. I did these steps, but you already know how to do the reduced row echelon form. I want to spend time to do it in details. So 1, negative 2. Okay. Now, row space of A, which is the non-zero rows, which is this one and this one. So we're going to say, let's say U1 equal 1, 0, 1, and U2 is equal 0, 1, negative 2. This is the row space of A, which is base for the row space of A. Null space of A is going to be the solution for the matrix, which is the solution. That's mean we have find x1, x2. So I'm going to say here on the side, x1 plus x3 equal 0. That's mean x1 equal negative x3. And the second one, we have x2 minus 2x3 is going to be equal 0. So x2 is going to be 2x3. Then let x3 equal t. That's mean x1 is going to be negative t, and x2 is going to be 2t. So the null space of t is going to be x1 is negative t, and x2 is 2t, and x3 is going to be just t. Base for the null space of A, we're going to let t equal 1. So here is the base. I'm going to call it v, which is negative 1, 2, and 1. Now this is the base for null space of A, and here is 2 bases for the row space of A. So we're just going to plug in these here. The first one is 1, 0, 1, and this one is going to be 0, negative, sorry, 1, negative 2. Negative 2. And the base for null space of A is negative 1, 2, and 1. One more thing, we need to prove that they are orthogonal. That's mean the dot product between U1 and V is supposed to be equal 0. Let's check the dot product between U1, which is 1 times negative 1, plus 0 times 2, and plus 1 times 1 is going to be negative 1 plus 0 plus 1 is going to be 0. And the dot product between U2 and V is going to be 0 times negative 1 plus 1 times 2 plus negative 2 times 1 and also equals 0. So that means row space of A is orthogonal on null space of A, the basis. And that's the proof for that. You don't have to write down anything for the proof. Let's check everything. There we go, we got it right. So the first thing they ask you to find a base for the column space of A. So before I start working on this one, now I need to reduce the matrix. So we're gonna reduce the matrix A by reduction 1, -1, 3, 5, 2, 1, 0, 1, -2, -1, -1, and 1. I'm just gonna say by reduction is going to be, let's see, here's the first leading entry. I'm gonna make this one 0, 0, 0. So 1, 0, 0, 0. And the rest is going to be 0, 1, 2 zeros here, 1, -2, 0, 0. Now, column space of A is going to be, here is the first leading entry and here is the second one. There is no leading entry here. That means column space of A, if you remember that, we're going to go back to the original matrix, is going to be span 2, these two columns. 1, 5, 0, -1. And the second column is going to be -1, 2, 1, -1. So this is the column space of A. That means we can say U1 equal 1, 5, 0, -1. U2 equal -1, 2, 1, -1. So when I do the dot product to prove orthogonal, I already have it here. Now, this is the first part. The second part, we need to find null space of A transpose. That means I need to find A transpose. So A transpose is going to be equal 1, 5, 2, -1. I'm gonna do it here. And -1, 2, 1, -1. And the third one is going to be 3, 1, -2, and 1. So this is the A transpose. Now let's work on A transpose cause the null space with the solution. That means A transpose, which is 1, 5, 2, -1, 0, 0, 0. And the second one is going to be -1, 2, 1, -1. And the third one is a 3, 1, -2, and 1. So by reduction, this one is going to be, I already have it here, is 1, 0, -5/7, and the 3/7 with the 0. And here is 0, 1, 1/7, and -2/7 with the 0, and all zeros here. So we need to find the solution that's mean. Let's work on here. X1, this is 0 minus 5 over 7 x3 plus 3 over 7 x4 is going to be equal 0. That means x1 is going to be 5 over 7 x3 minus 3 over 7 x4. That's it. We're just going to change the sign. And x2 plus 1 over 7 x3 minus 2 over 7 x4 is going to be 0. So x2 is going to be negative 1 over 7 x3 plus 2 over 7 x4. We're going to get x3 equal t or s and x4 equal t. That means null space of t transpose is going to be equal x1, which is 5 over 7, x3, which is s. So 5 over 7s minus 3 over 7t. And x2 is going to be 1 over 7 x3, which is the s. So 1 over 7 s and plus 2 over 7 x4, which is t. This is x2. It's going to be minus. This is minus, and this is plus. Okay. And x3 is going to be s, and x4 is going to be t. Okay. Now, which is this one, the null space is going to be equal as 5 over 7, negative 1 over 7, and 1, 0, and plus t. The second one is going to be negative 3 over 7, and 2 over 7, 0, 1. So we have two columns. With this one is going to be span. I'm going to say this is V1. So when I multiply, I'm going to multiply everything here by 7. So it's going to be 5, negative 1, 7, and 0. Or you can keep it as a fraction. It's up to you. And V2, which is the second vector, is going to be multiplied by 7, negative 3, 2, 0, 7. So here is V1 and here is V2. That's what we're gonna plug in here, but we need to prove when you do the multiplication, the dot product between U1, V1 equals 0. U1, V2 equals 0. U2, V1 also equals 0. The dot product between U2 and V2 equals 0 because it's orthogonal. So here we're just gonna write the row space of A, which is 1. Sorry, the column space of A, 1, 5, 0, negative 1. And here we're going to type the second one, which is negative 1, 2, 1, and negative 1. And null space of A transpose is going to be 5, negative 1, 7, 0. And another one is negative 3, 207. Let's check that. Here we go, we got it right. So example 4, they're telling you, let W be a subspace spanned by the given vectors, W1 and W2. Find a base for W complement. Let's check how we're gonna find the base of W complement. We have two vectors, W1 and W2. So example 4, we have W1, which is equal 1, -1, 4, -2. 1, -1, 4, -2. And we have W2, which is equal 0, 1, -3, 1. 0, 1, -3, 1. So now we need to find base for W complement. First of all, there's a rule. If you check the slides, it says W complement equal column space of A complement, which is equal, the same thing, is null space of A transpose. So I'm going to work on this one. Null space of A transpose. So let A equal W1 and W2. That's mean A is going to be equal matrix 1, -1, 4, -2, and 0, 1, -3, and 1. That's mean A transpose is going to be 1, -1, 4, -2, and 0, 1, -3, and 1. So here is the A transpose. Now I'm going to find the null space for A transpose. That means okay, A transpose, null space, which is A transpose with the 0. So here is A transpose 1, 0, -1, 1, 4, -3, -2, 1 with the 0, 0. By reduction, it's going to be 1, 0, 0, 1. And here, these two elements is going to be 1, -1, and -3, 1. Here is 0. So this is by reduction. We got this matrix. Now, we're going to find the solution for this one, which is x1 plus x3 minus x4 equal 0. So x1 is going to be negative x3 plus x4. And we have x2 minus 3x3 plus x4 equals 0. That means x2 is going to be 3x3 plus minus x4. So let x3 equal t and x4, let's do it s, doesn't matter, and x4 equal t. That means we're going to plug in everything here. So null space of A transpose is going to be x1, which is x3 plus x4. That's mean S plus T. X2, 3S minus T. And here's going to be S and T, which is equal S 1, 3, 1, 0 plus T 1, negative 1, 0, 1. That means here is the span. No space is going to be the base, which is the span to 1, 3, 1, 0 and 1, negative 1, 0, 1. That's it for this example. And they ask you to find the base. Here is the base. So we're just going to type here negative 1. Let's see. Negative 1. Here's negative 1. Because when I moved x3 negative x3, so here is going to be negative s, and here is negative. That means here is negative 1. Yep. Negative 1, 3, 1, 0, 1, negative 1, 0, 1. Negative 1, 3, 1, 0, and 1, negative 1, 0, 1. So now find a orthogonal projection of V onto the subspace W spanned by this vector. So the subspace W spanned by this vector. So let's first of all find an orthogonal projection, which is the projection. So projection of V to the vector U1 is going to be U1 times V, not times, dot product between U1 and V, and the dot product between U1 and U1, and everything with the U1. So it's going to be the dot product between U1 and V, 8 times 1 plus negative 3 times 1 over dot product between U1 and U1. So it's going to be 1 times 1 plus 1 times 1, and everything times the vector U1, which is 1, 1. So this one is going to be equal 8 times 1 is going to be 8 minus 3 over 1 plus 1. And everything is 1, 1. This one is going to be equal 5 over 2 times the vector 1, 1. So it's going to be 5 over 2 and 5 over 2. So this is the projection. And that's what I ask you to plug in. And it's orthogonal to this vector. Find just the orthogonal projection. So that's it. We're just going to put 5 over 2. And we're going to put here 5 over 2. The same thing, I think, with example 6. It's just to do the projection. But now we have U1, U2, and U3. So for example 6, we're going to find an orthogonal projection. So the projection of V onto W is going to be the projection of V to U1 onto U1 plus the projection of V to U2 and plus the projection of V to U3. So we're going to find, first of all, the projection of V onto U1, which is equal U1 dot product with the V over U1 dot product with U1 times U1 is going to be equal. So let's do the dot product between U1 and V. So 6 times 1 plus -4 times 1, so a -4 plus 8, so plus 0 plus 0. And U1 times U1 is going to be 1 plus 1 plus 0 plus 0. And everything times U1, which is 1, 1, 0, 0. So the result is going to be 6 plus -4 is going to be 2. 2 over 2 is going to be -1. So -1 times 1, 1, 0, 0. So the projection, the first one is going to be equal -1, -1, and 2 zeros. Now the second one, we're going to find the projection of V to U2, which is equal dot product between U2 and V and dot product between U2 and U2 times U2. This one is going to be equal U2 with the V. So 6 times 1, 6 plus -4 times -1 is going to be 4. 6 times -8 times -1 is going to be -8. -6 times 1 minus 6. U2 dot product with U2, so it's going to be 1 plus 1 plus 1 plus 1. And here is U1, sorry, U2, which is 1, -1, -1, 1. And this one equal 6 minus 6 is going to cancel. And it's going to be only okay. It's going to be -4 divided by 4 is going to be -4 divided by 4, -1. So -1 times 1, -1, -1, 1. And the result is going to be, we're just going to change the sign. So it's going to be -1, 1, 1, -1. Now the third part, we're going to do the projection of V to U3, which is equal dot product between U3 and V and U3 with U3 and times U3. And this one is going to be equal so U3 times V, that means this is 0 plus 0 plus with U3, 8 plus 6. And everything over 0 plus 0 plus 1 plus 1 times this vector and this one equal. This one is going to be 14 divided by 2. 14. That's 1 second. -6. -6 times 1 is going to be -6. So 8 minus 6 is going to be 2, divided by 2 is going to be 1, times this vector 0, 0, 1, 1. That means the result is going to be 0, 0, 1, 1. Now we're going to go back. The projection of W to the V, sorry, V onto W is going to be the first projection, -1, -1, 2 zeros. You can add the second projection to, which is -1, 1, 1, -1. And then you're going to add the third projection, which is 0, 0, 1, 1. And the result is going to be -1, -1 is going to be well, the first projection is on U1. This is not negative because 6 minus 4 is going to be 2. Divided by 2 is going to be 1. That means this is 1. And when you multiply, this one is going to be both 1. So that's changed our answer. So it's going to be 1, 1. Now it's 1 minus 1 plus 0 is going to be 0. 1 plus 1, 2. And this one is going to be also 2. And this one is going to be 0. So here is the projection of V onto W. So we're just going to type here. It's longer process, so you have to be patient. You're working on this one. Let's check. There we go, we got it right. Example 7, find orthogonal decomposition of V with respect to the W. So we already have V equal, example 7. V equal 4 to -1. And W equal span to this vector. Span to the vector 1, 1, 1. So I'm going to say this is W or U1, it's up to you. I'm going to keep it W. So the projection of V onto W is going to be V times W over W times W and everything with the W. So it's going to be 4 times 1, 4 plus 2 times 1 minus 1 over 1 plus 1 plus 1 and everything times W, which is 1, 1, 1. So this one is going to be 4 plus 1 is going to be 6, minus 1 is going to be 5 over 3. And everything times 1, 1, 1. So the projection is going to be 5 over 3, 5 over 3, and 5 over 3. So this is the projection. Now the decomposition, which is to the V on the W, is going to be V minus projection of V on 2W, which is equal, the vector V is 4, 2, negative 1, minus 5 over 3, 5 over 3, 5 over 3. And this one is going to be equal. 4 minus 5 over 3, that means it's going to be 12 over 3 minus 5 over 3. So it's going to be 7 over 3. The second one is going to be 2 minus 5 over 3. So it's going to be 6 over 3 minus 5 over 3 is going to be 1 over 3. The third one is going to be negative 1 minus 5 over 3. So it's going to be negative 3 over 3 minus 5 over 3. So it's going to be negative 8 over 3. That's it. This is the orthogonal decomposition. So we're just going to type here the projection is 5 over 3, 5 over 3, and here. And the decomposition is going to be 7 over 3, 1 over 3, and negative 8 over 3. Let's see what was the wrong thing. I didn't put here division. That's it for this section.